in the next subsection, we want to look at how to construct these automata that we've just used. I've explained to you briefly, if you're given such an automaton, how you can use it to search the text. And I motivated slightly a bit why this automaton contains enough information to do this task. But it's maybe not quite clear how to efficiently construct this automaton. So let's have a look at this. If you have this formal language background, you might think, why don't we use a simpler automaton, the non-deterministic finite automaton, instead of this deterministic one? The reason is that the non-deterministic automaton is really easy to write down. It is simply writing down the pattern like this as states and pretty much no other transitions. How does a non-deterministic automaton work? The non-determinism part is now that you have the option to have two arcs with the same character. And in particular here, you always have to decide, do you follow this track now or do you stay with the current A in 0? And the automaton doesn't help you. It just says, you figure out the way to decide where to go. And it accepts the string if there is any way to get to the accepting state. But if you took the wrong turn because you decided, oh, I'll stay and wait for another round, or you went running down this track and got trapped, that's your problem. You have to try to find any possible sequence through the states. And another way to say this is that at any point in time, you have to think of being in a set of states as opposed to a single state. So let's see how we can make sense of this, because it's a nice precursor to what the construction of the deterministic automaton does. So in principle, we could use this automaton. So again, this automaton is really easy to construct. You just write the pattern down, put states and one arc, and you add these transitions here where you can stay with every character in the 0 state. It's trivial to construct, and you can use it for string matching. Just there's a catch. But let's first see how, in principle, we can do it. And the key insight is you can, at any point in time, remember to be in a set of states as opposed to a single state. And whenever there's a way you reach the final state, so whenever there's a final state in your current set of states, you accept. It's a little bit like quantum computing from the spirit, but it's different in many ways. So you shouldn't mix up quantum computing and non-determinism, but it kind of has a similar flavor that there's parallel universes where you could have done different things. But that's where the analogy stops a bit. Let's do it on an example again, so same example as before, just to see how this works. We initially start in only the start state 0. So far, so good. Now if an A comes, I can go to state 1, but I could have also stayed, so I just do both. And after that, I'm simultaneously in state 0 or 1, where I could be in any of those two states. If I do another step A, it doesn't really bring me further from 1, so this branch that was in state 1 goes into the garbage state and dies out. But I've also been in state 0 in this point, so taking another step A brings me again to state 1 and back to state 0 at the same time. So after reading another A, I'm still in this state set 0, 1. If I now read a B, things get slightly more interesting. I can stay in state 0, but for the parallel universe where I was in state 1, I now move on to state B, state 2. And from there on, we get another branch. So if I'm in 0, 2 and I read an A, from state 2 I can go to state 3, that's great. From state 0 with an A, I branch into 1 and 0. So I'm now in 3 states, 0, 1, and 3. If I read a C at this point, these two die out. From 3, I cannot go anywhere, so end of the line. From 1, I die out, go to the garbage state. So the only thing that survives is state 0, which always survives because I can always stay there. So after this transition with C, I'm back to knowing nothing in a way. And then things repeat indeed. So I have A and A again. You will recognize the same as before. Then B, same as before. A, same as before. But now the next character is different. We're in the part of a match. So now if I read a B here, I have to go through all 3 states and see what a B does to them. From 3, I go to 4. From 1, I go to 2. And from 0, I can only stay in 0. So it brings me to the states 0, 2, and 4 after reading the B. If I read another A there, I'm now branching out into 4 different universes. All of these, so 4 goes to 5, 2 goes to 3, and 0 goes to 1 and 0. So I'm now in these 4 states. If I read a C now, 5 survives to 6, the other 2 die out, and 0 remains. But I'm still in states 0 and 6. And reading one more A brings me from 6 to 7. And that's all I need to know. The other states are interesting to know of. But as soon as you've reached the accepting state from any of these branches, you accept the string. Okay? Now it's a nice exercise to compare this table to the one before, but I'll leave that for you at home. So again, we can not only do this in this example, but in principle, whenever you have a non-deterministic automaton, you can construct the deterministic from it. You can even minimize the DFA afterwards if you feel like it. But this problem 2 from before kind of remains. The algorithm to compute a DFA from an NFA in general has a blow up where if you haven't seen this, think about this. You get a deterministic automaton by just taking the set of all the states in the deterministic automaton are all subsets of states in the non-deterministic one. And then you're doing exactly this simulation. You go from one set of states to another set of states. That's deterministic. The problem is there's many sets of states. So we're still not completely happy. But these 3 people, in essentially 2 independent ways, discovered that our string matching automaton is not a generic NFA. And indeed, if you apply this construction here, it doesn't actually lead to this exponential blowup. Or you can at least sneakily avoid it. And you can construct the DFA by adding one state at a time and avoid this blowup. And so what you construct is first an automaton for the pattern up to the first j characters. And then you add the jth character at the end and see what that does to the automaton. So this previous automaton, sorry for j-1, it will have states 0, 1 up to j-1. It will have this general shape, and it will have various arcs going back. And so if we want to go now to AJ, the automaton for the pattern with one more character at the end, what we'll always have to add is the new state j. And that just gets the transition pj. And we also need the failure arcs. So what happens if I am, so remember here in the previous automaton, these were not really there. Instead, they were loops on the accepting state. Sorry, I have to make the picture a little bigger. This is always a mess with the indices. So we have j minus 1, but we also have state j, which is one after reading the previous character brought us here. So this one has a failure link somewhere back there, but this one didn't. Now what I add to the new is state j plus 1, which is reached by the jth character. And I have to find out where do these go back. So instead of staying there, I now have to find where does this branch back to if I'm reading a character that's not the right one in the pattern. Okay, so I need a new state. This transition is easy, but I also need the other transitions, and these are the tough ones to figure out. And remember what it meant to be in a certain state. It meant we've seen a certain prefix, and that was the longest that we know that we could have seen up to this point. So let's go through this. So delta is the target of this arc. Delta jz means I'm in state j, and I'm reading a character c. And now I have to jump back. So these are only for the arcs that don't bring us forward. And that leads to a state delta jc. That's the target of this arc. And we want to know where this is. Now, remembering the invariant, it is the state, so it's the length of the longest prefix of this text, of this thing, that we can find, so that it's always also a suffix of this. So I think this is best shown in a little picture on the side. So we know the text currently looks like this. We have P0 up to J, but excluding J. And we read one more character C, and it's not the right that we would have expected here. And now we're trying to shift the pattern forward by as little as possible, so that I here have the same, but with the first character omitted, and again the character C at the end. And I want to shift this forward so that these characters all match. Okay, that's the goal. Now the insight here is, so the insight really is into this, in this equality. How much do I shift this forward? That is something that the smaller automaton can tell me. Because this never uses the last character of the pattern. It only uses up to the jth position. So I can use the automaton I already know and simulate that automaton to tell me what should be the state where I'm supposed to be at now. So you can simulate the old automaton, aj minus 1, on this text. Just suppose you start reading the text again, but you omit the first character of the pattern. And so we'll see how this works in a second. Taken as this, so this would work. You can construct the automaton like this. But it seems each time you compute one more arc, you have to simulate the automaton. So you have m states in total, you have sigma arcs per state, and each time you would have to simulate the automaton one smaller with something on the pattern, so that would take another m time. And so this seems a bit expensive. And there's another little trick. The second insight from this algorithm is that we don't have to run this automaton from scratch, because if you did this simulation, it would always start with the same prefix, P1 up to J. And only the last character differs. We have different characters C, so we need a different arc here for the different characters in the alphabet that are not the correct one. But the simulation would always use the same prefix. So we don't really need to do it. We instead can just remember what is the second to last state and go one step from there. And so that's what we can do. We maintain a state X, which is the state where we would have gone with this, reading this in the automaton. And from this state, we go one further arc with all the different characters. And then we put these into the delta table. There's a nice graphical way to show this, and it's nicely shown in this video. So I just show you this instead of trying to recreate slides for it. I hope the sound is audible.
Well, let's take a look at a demo that does the full construction for the Kmp Dfa. Here goes. Again, one state for every character plus an except. Match transitions are easy. We build those. And we're going to start at position 0. And the mismatch transitions are easy. Now when we move over, X is, when we're in position 1 of the pattern, X is where we would be if we started out without that character, which would be the empty string. We start out with just filling in zeros. For state 0, and we can do that without any further reasoning. But now we've got X initialized. So now what we need to do is fill in the mismatch transitions for state 1. So what are they? They're what would happen if we found those characters and we were in state X. If we found an A, we'd go to state 1. If we found a C, we'd go to state 0. And maybe you notice that's just taking the entries corresponding to the entries we need from X's column and putting it in J's column. That's all it is. And then we need to update X, which is where it would be if we matched a B. So we'll stay in, X will stay in state 0. So now let's look at state 2. So we need to fill in what would happen if we got a B and what would happen if we got a C. Well, it's what would happen if we were in state X and we got a B or a C. So all we do is move those 2 zeros over to column 2. And then don't forget we have to update X, and X goes where the machine would go if we saw an A, that transition from 2 to 3. So we just move X to state 1. So now we have X in state 1 and we're doing position 3. And now you can see how really simple the algorithm is once it gets going. Now the mismatch transitions are A and C, and that's what we have to fill in for column 3. But those mismatch transitions were already computed. That's where X would go. That's where it would go if we happen to be in state 1. So we move the 1 and 0 from column 1 over to column 3. And again, we update X. And when we see a B, X goes to state 2. And again, you can check what is X supposed to be. It's supposed to be where you would be if you started the machine on the pattern with the first letter cut off. So it's supposed to be where would you wind up if you got BAB, and that's a check. All right, so now it's straightforward. State 4, we have to fill in B and C. We go to X's column and copy over B and C from X's column. Then we update X. That's if you see an A, you go to state 3. Now we're ready for state 5. We've got X all computed. And we need to do A and B, and we get those from X. If it's an A, it's a 1, and if it's a B, it's a 4. It's just moved them over. And then when we do the C and get the except, there's no mismatch. That's the, we do update X to get ready, but when we get to state 6, we're done. And again, it's just as a double check, X is where you'd be if you saw B, A, B, A, C. That's the construction of the Knuthmore DFA.
All right, the audio wasn't great, but I can try to smuggle in the original video in the recording if you want to watch it again. I think, I know it's maybe a bit slow, but the construction is very nicely shown, that it's very simple. If you look at this matrix of the transitions, you just have to copy columns. So executing it by hand is maybe the better way to understand what's happening here. Let me wrap up this subsection by looking at how well these methods work. So this might not have been obvious from how I showed this on the examples, but if you've given this automaton, finding the pattern in the text is really feeding the text through the automaton. And this takes n steps because it's a deterministic automaton. So in each step, you just need to find what is the transition I have to take. That brings you to some other state, and then you keep going from there. You can do this with table lookups for this delta table that you've seen in the video. Building the DFA necessarily needs as much time as you need arcs to fill. And there's m states, sigma arcs per state. So that's the number of arcs, sigma times m. And with the construction from the video, it actually is constant time per edge. So in total, if you sum this up, we spent m times sigma time on the pre-processing stage, plus n for the matching, so that's the total time. That's already much better than n times m if m is not super small. And even if m is fairly small, the pre-processing step is also fast, right? The space is what you need for this transition table of the automaton. So again, you need one entry for each arc. M times sigma is the number of arcs. So that's roughly the space you need for executing this algorithm. In terms of the time, this is actually really hard to beat for the matching part. And because you do one table lookup for each character in the text. And at least if the alphabet is small, this is also the best possible total time. The big downside is the space overhead. And think again, so sigma is the size of the alphabet, which can be small if you have something like DNA, but it could be the Unicode alphabet, which is 150,000 characters. So you're trying to find a little string like love in all the works of Shakespeare, and you spend, I don't know, a megabyte of space for building this lookup table, and you have to fill this first. So you're probably halfway done if you just use the brute force method. So this doesn't sound too scary using 1 megabyte of memory, but remember it grows with the pattern length. And it's just a very, very basic task that you might use many times. So you want something really efficient there. So we'll try to work on this a bit more. Especially bringing the space down. And that's what then is called the Knuthmore spread algorithm. I think we'll reserve this gem for next time, where we have fresh energy. It'll bring all these ideas together and just take this idea of the automaton one step further to get rid of this dependency on sigma.